Video number 8 plus. The missing mass enigma. Following the recent launch of the Euclid Space Telescope, it is a good time for a video about the missing mass enigma. Maybe you will not understand the title at first because in the recent decades you have been hearing more about dark matter, which is a different word for the same thing. This comes from two circumstances. First, the founder of the enigma himself spoke about dark matter or hidden mass from the very beginning of the case. Second, the vast majority of astronomers today believe that the answer to the puzzle lies in the presence of dark matter, some of which has already been identified and some of which still has to be discovered. It is important to retrace the history of this case because this enigma has led to questioning our knowledge of the gravitational force. The case began in 1933 with a paper by the astronomer Fritz Zwicky, the co-discoverer with Wilhelm Bard of the concept of neutron stars and the creator of the term supernova. Fritz Zwicky was working on Hubble's method of evaluation of distances of galaxies from their redshift related to the expansion of space and the Doppler effect, while studying the motion of galaxies in the so-called Coma cluster, located about 300 million light-years from the solar system. He found a curious anomaly. From the overall luminosity of the cluster, and knowing the distance from it, deduced from the average redshift, Zwicky could estimate its total mass under the assumption that the mass-to-luminosity ratio was the same as that previously calculated for nearby galaxies. After evaluating the rotational velocity of a few galaxies, taken at random among the 800 or so in the cluster, he discovered that on average they rotated much too quickly, as if the cluster were 400 times heavier than what he had calculated from its light. In a later paper from 1937, after correcting the mass-to-luminosity ratio, he still found a rate of 125 instead of 400. Zwicky concluded that the cluster had a large amount of hidden mass located within or between galaxies, which was later called dark matter. Several decades later, part of this mass was discovered, consisting mainly of clouds of gas and dust. We have also corrected the distance of the cluster, located at 300 million light-years, whereas in the 30s this distance was estimated at 45 million light-years, due to a mistake in the evaluation of Hubble's constant. After all these corrections, there remains an unexplained discrepancy of a factor around 5 between the calculated mass and that which can be deduced from the rotational speed measured by Zwicky. You may be wondering, what is the relationship between the rotational speed and the mass of the cluster? To understand this, I suggest you consider a much simpler system formed by a central mass and another mass rotating around it in a uniform circular motion. This part of the video, although very simple, can be skipped by people who do not have the necessary mathematical knowledge. It is enough for them to remember that the behavior of the large system, although very complex, has, assuming that it is in dynamical equilibrium, computable characteristics whose form can be guessed from a much simpler configuration where the total mass of the cluster is concentrated at the center and a single, lighter object revolves around it. For the reduced system, let us describe the motion in the complex plane, taking the central point as origin. The trajectory of the external object, remaining at a constant distance R from the center, is described, if necessary by changing the origin of time, by the formula u of t equal capital R exponential of I omega t. On the other hand, Newton's law gives the acceleration gamma equal u double prime equal minus capital G capital M u divided by capital R to the cube equal minus gm divided by r square exponential of I omega t. Whereas the first formula gives u double prime equal minus capital R omega square exponential of I omega t. By identification, we obtain omega square equal capital G capital M divided by capital R to the cube. Finally, the scalar velocity v is given by r omega equal capital G capital M divided by capital R to the power 1/2. A mass 400 times too large therefore corresponds to a velocity 20 times too high. A mass 5 times too large corresponds to a speed approximately 2.2 times too high, which is much less spectacular. Solving capital M, the equation gives capital M equal v square capital R divided by capital G. In his more evaluated calculation based on the Virlow theorem applied to the n-body problem, Zwicky finds that capital M is comparable, up to a factor not very different to 1, to capital V square times capital R divided by capital G, where capital V square is the mean of the square of the velocities of the galaxies. Coming back to the main point, you can see how, as observations and experiments progress, something that was at first totally puzzling becomes less and less bizarre. One can even imagine that during our century, the rest of the missing mass will be discovered little by little, since we have already gained a factor of 100. Of course, that hidden mass case does not stop there, otherwise there would have been no reason to talk about it. In the 70s, a new problem appeared in astronomy. The American astronomer Vera Rubin noticed that the distribution of rotational velocities of the stars in relation to their distance from the center of the Andromeda galaxy followed a law quite different from that provided by theoretical calculations. This velocity should have decreased quite strongly when approaching the edge, whereas the observation indicated a speed practically independent of the distance to the center. In popular text, the analogy is often made with Kepler's third law, t squared over 8 to the cube equal constant. But this analogy is not very relevant because the mass of the galaxy is distributed more or less continuously from the center to the boundary. It remains that the calculation of the physicist suggests a velocity curve very different from what was observed. Vera Rubin therefore thought that the best explanation would be, as in the case of Zwicky's paradox, to imagine the presence of a gigantic halo of dark matter surrounding each galaxy, and from this count the percentages of dark matter in the universe that everyone can find on the web. Unfortunately, all diagrams that we can find now combine dark matter with dark energy, an even more hypothetical claim which has nothing to do with gravity and is related to completely theoretical considerations on the large-scale structure of the observable universe. Here, it turns out that a large cloud of dark gas, probably made of the most classical matter, without exotic particles, was recently discovered around the Andromeda galaxy, M31, precisely the one whose examination by Vera Rubin provoked extensive new research into dark matter and even non-baryonic dark matter. Another possible explanation for these two gravitational discrepancies have been suggested by the physicist Mordechai Milgram, a modification of Newton's law for very large distances. But there are many other possible explanations, and in fact, the problems with clusters and galaxies may have completely different explanations. As we shall see in a forthcoming video, there are many ways for mass to become invisible, including for standard matter and even luminous matter, depending on the way it is distributed in space. The hypothesis of an exotic dark matter has also been reinforced by some problems connected with gravitational lenses, and this is one more reason why the specialists go on believing in its existence. Since the Euclid Space Telescope was devised to work on the dark matter and dark energy hypotheses, we shall be looking forward to its observations planned for the near future.